Hi everyone, I am Yongrong, currently a postdoc in Andreas Stoller's lab at Stanford. Firstly, I would like to thank all the organizers for this wonderful meeting and inviting me to present the work here. Today I'm going to talk about probabilistic neural transfer function estimation with Bayesian system identification. In sensory neuroscience, neuronal responses are driven by the external physical stimuli, and this relation has been characterized by the tuning curves or receptive fields. Here I show you an example receptive field of the neuron in the visual cortex of a cat, demonstrated by the Huber and Wiesel in 1950s-60s. Such stimulus response functions have been estimated by neural system identification methods. Here shows the stimuli, and you can record the neuronal responses to these stimuli. With such stimulus response data, you can train a model. After training this model, you can use it to predict the responses to unseen stimuli. Classically, these approaches use linear nonlinear Poisson models and their variants. Here shows an example. The linear nonlinear Poisson models learn the linear weights and the nonlinear functions for each neuron. More recently, deep neural networks have shown great success in predicting responses along the ventral visual pathways, including the retinal, primary visual cortex, and the higher visual areas. Here shows convolutional neural network. The input layer is the stimuli, and the hidden layers are the convolutional layers and the nonlinear functions. And the output is the responses. After training this network, you can perform in silico experiments. It has been shown that these models can generate specific stimuli to identify novel neuronal properties from a high-dimensional space. For example, closed-loop experiments demonstrate that performing gradient ascent can generate most exciting input, the MEIs, to drive neurons activation optimally. Here shows 9 example MEIs in the visual cortex of mice. The lower is the confusion matrix, the x-axis is the MEI images, and the y-axis is the neurons. We can see that most of the neurons are trained optimally by the respective MEIs. Yet these models demand significant amounts of stimulus response pair data for the training. Due to limited recording time for each experiment, the amount of data for fitting length is restricted. This introduces uncertainty about the learned MEIs. Therefore, we propose Bayesian system identification to estimate the response features of neurons with uncertainty. Here, the top row is the biological neuron. We want to get the MEIs. The traditional point estimate methods can predict the response and generate the MEIs, but we don't know the statistics of these MEIs. And the Bayesian methods learn the full distributions of the model weights. In this way, we can generate the MEI, infinite MEIs, and compute the significance. So we test whether incorporating uncertainties by learning the full distribution of model parameters is beneficial for learning neural representations. To this end, we built a DNA model to predict responses to unseen visual stimuli by using variational inference to estimate the distribution of network weights. I will not go into the technical details, but if you're interested, we can discuss after the talk. Here I show you one hyperparameter, beta v. This is the distribution of the mean of the model weights. We can see that when we increase the beta v, the distribution concentrated around 0. We compute the proportion of mass falling near 0 for different beta v's within the certain thresholds. We see that it's increased, that means the sparseness increase. Therefore, the hyperparameter, the beta v, serves to tune the model capacity via weight sparseness for data. Here I show you example recorded responses, the gray color, and the predicted response from the baseline, the black one. The baseline is it's a convolutional neural network without any regularizations. And the L2, L1, this is a convolutional neural network with L2 and L1 regularizations on different model layers. The green one is our variational approach, and the blue one is MC for our model. We also show the MEIs and the standard deviation of MEIs. We will talk about this more later. We can see that these standard deviations are not uniform across video space. Therefore, these models yield antagonistic center surround and kappa filters in the local region, reminiscent of neural representations in early video processing. We next evaluate the model performance. We use root mean square error, log likelihood, linear correlation as metrics. We compute it for models trained by half of the data and full of the training data. For example, we look at this log likelihood. The green one is our model. We see that the value is higher than the other models. Also, when we increase the beta v, we see that the linear correlation suddenly drops. So, the superior equivalent performance of our variational approach suggests that incorporating weight uncertainty is beneficial for predicting neural responses. A model predicts responses with uncertainty. Next, we perform standard calibration analysis. In this way, we can address questions like whether the predicted 90% credible interval includes the recorded responses 90% of the time. Here the x-axis is the predicted confidence level, and y-axis is the observed level. For both variational MC draw, we can see that the predicted levels are higher than the observed ones. That means these two models are overconfident. Next, we examine whether there's a relation between variability of transfer function and the model performance. Here, when we increase the beta v, we observe the increase of the MEI variance. With this increase, we see that we observe that the correlation drops. So it is a negative correlation between the MEI variance and the response CC. Therefore, a model with higher predictive performance had higher confidence on the learned transfer function. We also apply our method on a second dataset. With small training data, we can see that these models had better performance. We see that our variational method, the green one, has better or comparable performance with other models. Also, with more training data, the MEI variance also decrease. So again, a negative correlation between the overall MEI variance and the model performance. So when more training data was used, the predictive model performance increased, while the overall MEI variance decreased, with a negative correlation between a model level. Additionally, we examined the difference between the model performance for the variational model and the L2 plus L1 model. When the training data size increase, you see that the difference increase and then decrease. Here is a scatter plot for when the difference is largest. Each dot represents one neuron. We can see that the variational model had larger values in the L2 and plus L1 model for most of the neurons. Therefore, compared to a traditional method, a Bayesian approach with weight uncertainty yielded higher predictive performance with a higher data efficiency. We also test whether the effectiveness of the MEIs generated by our method. Here we use the verified MEIs from previous literature. I show you 6 neurons here. We compute the activations, the neuronal activations driven by these verified MEIs. Here we show distribution because we can sample the model weights multiple times. We see that these green ones, the respective MEIs, the activation is larger than the gray ones. We did this for other neurons. From this confusion matrix, you can see that more than 90% of neurons were elicited by the respective MEI with more than 80% of highest activity, suggesting that our Bayesian method works effectively well. Next, we performed the in silico experiments with these derived MEIs. Here I show you 3 example neurons. The MEIs from the point estimate model and the MEIs from the variational model. We also showed the standard deviations of these MEIs and the significance map. The significance map means whether the posterior of each pixel value differs significantly from 0. We also showed the distributions of the activations for the neuron 1. This is a distribution. The green one is a distribution because we can sample the model weights multiple times. We can see that the maximum of this activation, the green one, is larger than the red one. The red one is computed by the point estimate method. We did this for all the neurons. Here shows on the scatter plot, each neuron is 1. Each dot is 1 neuron. You can see that most of these neurons have higher activations for the variational model compared to the L2 plus L1 model. So, our variational model allows statistical test for the derived response functions and yielded the stimuli driving neurons better than traditional methods in a limited data regime. Here limited because you see this difference significantly when we use 40% of the data, but when we use full of the training data, it's not significant. In conclusion, we incorporate weight variability in deep neural networks for identifying neural response functions with uncertainty. Our method can achieve higher or comparable performance or neural prediction with a better data efficiency. Also, our approach allows to estimate neural features with credible intervals and run statistical tests for the derived MEIs. In the end, the simulation experiments show that our model generates stimuli driving neuronal activity significantly better than traditional models. Lastly, I would like to thank all the collaborators, Nan, Isabel, Fabian, Alex, and Thomas. I would like to thank all the support from all the funders. Thank all the lab members from Euler lab, Sinz lab, and the Tolliers lab. Thank you very much.